All right, we have another um, definite integral involving an absolute value. And again, we're not going to try to graph this. We just remember the basic concept. When in any x value where this expression, which is inside the absolute value bracket, gives me a positive, I just go ahead and evaluate the same expression. However, any value of x that generates a negative value for this expression, I evaluate the opposite, which would be x minus x squared. Okay. So what I've got to do is figure out, uh, when does x squared minus x equal 0? So x squared minus x equals 0 when what? Well, when x times x minus 1 equals 0, and that's going to be at x equals 0 or 1. Okay? Simple as that. At those two values, this expression equals 0. So I want to explore values greater or lesser than 0 and 1 with a number line. And that number line will help me understand which expressions I use in which intervals. Okay, so here's 0 and 1. And I'm going to put test values into the two different factors, x, and I'm going to write down the factors this way. We've done it other ways, but I think this is kind of a good way to do it sometimes. All right, and I'm going to evaluate and see where do I get a positive or negative value for this expression, x squared minus x. So I'm going to pick a value less than 0. I'll just pick 1. And if I pick 1 and put 1 inside of x, I would get, well, that's a positive value, right? Oh, excuse me, that's a negative 1. So sorry. So less than 0, I pick a negative 1. And for negative 1, that would give me a negative value. And negative 1 minus 1 gives me a negative value. Okay, so those are both negative. Negative times negative would give me a positive. So for any value of x less than 0, this expression gives me a positive value. Okay, so how about any value of x between 0 and 1? Let's say a half. If I drop a half into x, I'd get a positive value. If I drop a half into x minus 1, I'd get 1 half minus 1 be a negative value. And a positive times a negative would give me a negative value here. So any value of x between 0 and 1 gives me a negative value for this expression. And what about values of x greater than 1? If I drop a 2 into x, I'd get a positive, and a 2 into 2 minus 1, I get a positive. Positive times a positive is a positive. So any value of x greater than 1 makes this expression positive. So again, if I'm looking at values greater than 1, I can just evaluate x squared minus x, and that's the same as evaluating the absolute value. Likewise, for any value of x less than 0, this expression here is still positive, so I can just evaluate again x squared minus x. But if the value of x is between 0 and 1, in that interval, I need to evaluate the opposite of x squared minus x, or x minus x squared. Okay? So I can replace this definite integral of an absolute value function now with basically three separate definite integrals. One's going to go, I still have to cover the full interval from negative 1 to 2. So one's going to go from negative 1 to 0, and then 0 to 1, and then 1 to 2. So here we go. So this equals the definite integral from negative 1 to 0 of x squared minus x dx. Make this 0 nice and neat here. And I'm going to add that to the definite integral from 0 to 1 of x minus x squared. It's the opposite expression, dx. And then the final definite integral is from 1 to 2. That's going to be of x squared minus x dx. Okay? So we've covered the entire interval from negative 1 to 2, but I've had to do with three separate definite integrals. And in two of them, I can evaluate this same expression because in those intervals, this gives me a positive value, and the positive value is the same as the absolute value. And only between 0 and 1 do I have to use the opposite. So now I'm just going to go ahead and evaluate these three separate definite integrals. Okay. So the antiderivative of x squared is x cubed over 3. And the antiderivative of x is going to be x squared over 2. Okay. And that's going to be evaluated from negative 1 to 0. The next antiderivative, again, the antiderivative of x is x squared over 2. Now, in this case, minus x cubed over 3. And we evaluate that from 0 to 1. And the final definite integral, x squared, antiderivative is x cubed over 3 minus x squared over 2 from 1 to 2. And again, it should be no surprise that each of these antiderivatives look pretty similar, because we're just taking variations on the original expression, either positive or negative, just reversed or the same order. Okay, now let's do the evaluations. So this equals, and again, keep it simple, nice, straightforward, keep the square brackets in place so we know what we're doing. So I drop a 0 in here. So that's going to be 0 minus, that's just 0, okay? Minus what? Well, if I drop a -1, well, -1 cubed is -1/3, okay? -1 times squared is going to be just 1, but it's minus then 1/2, okay? Um, oops, I'm going to put a square bracket there. Okay, so again, I'm going to keep the square brackets so that I have each of my separate calculations clearly identified. Now, I evaluate this one at 1 and 0, so that becomes 1/2 minus 1/3. Then evaluate at 0, it's just minus 0, okay? And then finally, evaluate this final expression between 1 and 2. So I drop the 2 on there, and I'm going to get 2 cubed is 8/3 minus 4/2. And then I drop a 1 in, I get 1/3 minus 1/2. Okay? All right, now, a whole lot of fractions. You want to go very slow and carefully here. What I'm going to do is simply go ahead and pick up all of the fractions, being very thoughtful about the sign of each one, okay? So the 0, I'm not going to bother writing down here, but I have to distribute this negative sign, so I'm going to get a positive 1/3, right? And then the negative, so positive 1/2, all right? And that finishes off that first square bracket. Plus 1/2 minus a third, so 1/2 minus 1/3. Okay, and that finishes off that square bracket. And then on the final one, I've got 8/3 minus 4/2, 8/3 minus 4/2. And then I have to distribute the negative minus 1/3, and then a negative plus 1/2. Okay. All right, boy, that's a lot of fractions. A couple of things. I see a couple of things I could cancel out right away. I see a positive third and a negative third. I don't see anything else I can cancel out. I can cancel those two out right away. All right. And I'm left with a couple halves and some thirds. So the common denominator is going to be a 6. So I'm going to go ahead and rewrite all these fractions without the brackets, convert each one to something over 6. So 1/2 is 3/6. Make that nice and neat. That's 3/6. Plus another 3/6. Okay. 8/3 is going to be 16/6 minus 4/2. That's going to be 12/6 minus 12/6. Minus 1/3 would be minus 2/6. And plus 1/2 would be plus 3/6. Okay. All right. Now, wow. It's what I like to do sometimes. I get positives and negatives. I'm just going to go ahead and gather up all the positives. Plus 3, plus 3, plus 16, plus 3, right? So 3 plus 3 is 9. So 3 plus 3 is 6. Plus 16 is, so 3 plus 3 is 6. Plus 16 is 22. Plus 3 is 25. So that's 25/6, okay? And then I have minus 12 minus 2, minus 14, oops, not 16, minus 14/6. Minus 14/6. So 25 minus 14, that's going to be 11/6. And that is the answer, okay? And again, just to review, what we did is we took the moment to figure out where does this expression equal 0, set up a test line, a number line test, figure out for what values of x does this expression have a negative value, and in those intervals, I look at the opposite of this, and wherever it has a positive expression, I look at just the expression as it is, and in that way, I end up with 3 separate definite integrals, but none of them has to work with an absolute value. So it's a little more addition and subtraction, but I find a way to get down to my answer of 11.6.